Hello and welcome to Stat 441 at Virginia Commonwealth University. In this lecture, we will learn about sampling distributions of sample statistics. Okay. So let's think about it. Let's say we have a sample, which is n measurements that we have from a population, and let's call these observations y1, y2 through yn. And then consequently, we will calculate sample mean x bar from this sample. We can calculate the sample variance s squared, and we can calculate other statistics for uh, this sample. And these statistics will be functions of the random variable. Now, when we start drawing inferences in later chapters about population parameters, we will use these sample statistics to draw those inferences. Okay. So the primary reason that we started talking about probability and then other probability distributions in previous chapters was for us to be able to find the properties of the probability distribution of these statistics. So basically, these probability distributions for the statistics, they are called, or it is called, the sampling distribution. So for example, we calculate a mean for the sample, x bar. How is the sampling distribution? What is this distribution of this mean x bar? So basically what that means is that if we draw a lot of samples from this population, let's say we have a population with some mean mu and standard deviation sigma, and we draw, let's say, 50 samples from this population. And then we calculate the mean x bar for each of these samples and make a histogram for those 50 mean values. That is the sampling distribution of x bar. Okay. Similarly, for other statistics, if we draw a lot of samples, calculate that statistic for each sample, and then make a distribution, that will be the sampling distribution for a statistic. Now, just like a single random variable, the center of this distribution will be the mean. So the mean will be the expected value. We will call it the expected value. The standard deviation of this distribution will be called the standard error of the statistic. So basically, sampling distribution of a statistic is its probability distribution with what the shape of the distribution is, what is the mean or expected value of the distribution, and what is the standard error or standard deviation of that distribution. Now, one of the main statistics that we use a lot is x bar, the sample mean. And for the distribution of the sample mean, we have the central limit theorem, which helps us describe the sampling distribution of the sample mean x bar. So again, let's say we have a sample of n observations, y1 through yn, which comes from a population with a finite mean mu and variance sigma square. Now, if n is sufficiently large, which in this case 15 is considered large enough, the sampling distribution of the sample mean can be approximated as a normal density function. So that's the central limit theorem, that if we pick a sample from a population and then make a distribution for the mean values, then it's normally distributed. Also, the mean and standard deviation of this sampling distribution can be given by mu y bar. So mu of the y bar mean is equal to the sample mean, the population mean mu. And this standard error of this sampling distribution, so sigma y bar, is equal to sigma divided by square root of n. So it depends on the sample size. So larger the sample size, smaller the standard error because it's in the denominator. Okay. Now this sampling distribution is a very useful distribution that we will use in a lot of inference techniques. It is an example to see how the central limit theorem can be used. So here's the example. This is a study which was conducted at Luton Airport to assess the suitability of concrete blocks as a surface for aircraft pavements. The original pavement quality concrete of the western end of runway was overlaid with 80 mm thick concrete blocks. A series of plate bearing tests was carried out to determine the load classification number, a measure of the breaking strength of the surface. Okay, so this is some basic information. Now, let Y bar represent the mean LCN of a sample of 25 concrete block sections on the western end of the runway. So we have picked a sample of size 25, and the mean of this sample is Y bar. Prior to resurfacing, the mean LCN of the original pavement quality of the western end of the runway was known to be mu is 60 and sigma is 10. So this is for the population, mean and standard deviation for the population. If the mean strength of the new concrete block surface is no different from the original surface, describe the sampling distribution of Y bar. So when you have to describe the sampling distribution of Y bar, we need three things. We need, first of all, it should be a large enough sample. So 15 plus sample size is good enough. Or if the population originally is known to be normal, then we don't need to worry about the sample size. Here we don't know what the actual shape of the distribution is for the population. So we will apply the central limit theorem because the sample is large enough. So the sampling distribution of the mean of LCN is approximately normal, okay? And mu Y bar will be equal to the population mean, which is 60, and sigma Y bar will be sigma divided by square root of n, which is 10 divided by 5, or it is 2. So what is the sampling distribution of X bar for a sample of size 25? It is approximately normal with a mean of 60 and standard error of 2. Okay, so this distribution now can also be used to calculate the probability for the mean Y bar. Let's get in the example. If the mean strength of the new concrete block surface is no different from that of the original surface, find the probability that the sample mean LCN of the 25 concrete block sections exceeds 65. Okay, so we have the sample of size 25 and we are trying to figure out the probability that Y bar is greater than 65. See, this is different than what we did earlier. In earlier chapters, we were looking at just Y. Now we are looking at Y bar for a sample of 25. So Y bar is greater than 65. So we make the Z-score transformation. So instead of mu and sigma, we will use mu Y bar and sigma Y bar, which is 65 minus 60 divided by 2. So probability of Z greater than 2.5. Again, using the Z table, we can, if we look up 2.5, gives us 0.4938. We need the probability for greater than. So 0.5 minus 0.4938, which is 0.0062. Okay, so that's the central limit theorem and how we can use the central limit theorem to find the sampling distribution of X bar and the probability for X bar. Now, there are other sample statistics that we will use, and there are sampling distributions that are associated with that. So here is a quick introduction of some other distributions. We will discuss these in detail once we start using them in chapter 7 and 8. There are probability distribution tables associated for each one, and then specific statistics where we use these distributions. So three main distributions. So the first one is the chi-square distribution, second T distribution, and the third one is F distribution. So let's look at the chi-square distribution first. So chi-square distribution is if a random sample of n observations is selected from a normal distribution, then the chi-square distribution, this is the sign for the chi-square distribution. And this distribution relates to the S square and sigma square of the distribution. So the population variance and the sample variance. This is the shape of this distribution. It is not symmetric. Again, it is used to make inferences about the variance and standard deviation. The next distribution that we will be using is the t-distribution. So here is how it is related to the z and the chi-square distribution. The t-distribution is z divided by square root of chi-squared over nu, which is the degrees of freedom, and this is n minus 1. This distribution is basically used when we do not know the population variance, and and it will be used when we have a very small sample size. So we can't use the central limit theorem, so we will use, instead of the z distribution, we will use the t distribution. Okay, so as you can see here, this is the shape of the distribution. It is bell shaped, just like the normal distribution, but slightly heavier tails here, or slightly wider tails compared to the normal distribution. Here is another relation of the t distribution with y bar and s. So as you can see, this is similar to the z-score transformation. Again, that's why we have the similar shape, except it depends on s, which is the sample standard deviation, and it changes if we have a different sample size. So therefore, the t distribution depends on the sample size. Basically, we have replaced the sigma with the s here. Here's the last one that we will be using, the F distribution. It is basically the ratio of two chi-squared distributions. So this will be used when we are trying to make inferences about two population variances. So we need to figure out the ratio of two population variances. That's when we will use this distribution. Okay, F distribution has 2 degrees of freedom, nu1 and nu2. So this depends on the first sample size, and this depends on the second sample size. Again, this has a distribution table associated with it. We will be using that. And this distribution will be used to make inferences when comparing two variances or even standard deviations. Okay, here is the shape of this distribution. Again, it is not symmetric. Okay, so this was just a quick introduction of the distributions that you will be seeing in the future. And that's all for this lecture. Thanks for watching.